Okay, in this video, I'm going to do a walkthrough of the new SPS version 2, SPS for studio power switching, meaning that I'm trying to give you the kind of headroom you'd have on studio gear in a guitar pedal, manage that power system, and obviously turn the pedal on and off. So I'm going to walk you through the circuit in its separate chunks. So here's the Eagle schematic. Let's go ahead and zoom in on this upper section, the thing that makes it different from the last one, and that, the main thing, not the only thing, is this charge pump. Simply all it's doing is doing a voltage inversion. So it's taking whatever voltage you're inputting and invert it. So if you input 9 volts, negative 9 volts comes out. 18 volts, negative 18 volts. I've done this before, but the difference about this chip is two things. Number one, it runs on a really high operating frequency. It's like 500 kilohertz. So using it with digital pedals that have their own clocks or bucket brigade delay chips and stuff like that, that digital whine or heterodyning interference that you would get with some charge pumps that run at a lower frequency, you shouldn't get here because this runs at such a high frequency that you won't get that audible interaction. You also get much less ripple for that reason as well. The second thing about it is the chip that I used to use that ran at 35 kilohertz, and this one's 500. That one also was limited to an absolute maximum of 16 volts, and so you couldn't plug in 18 volts. This one, 18 volts, no problem. So anywhere from 9 volts, 18 volts, you use the power supply that you want to use, and it will invert it. I should note that it's not a perfectly efficient inversion, so you do lose a little bit of a voltage. So if it's 9 volts positive, it's probably like negative 8 point something, depending on the whole circuit, volts on the other side. But it's pretty close, as far as like how you would design, it's not going to really impact designing from it and using it. So those two massive advantages. The big disadvantage is that it costs a lot more, and that you really can't solder it by hand. The package needs to be something that is done by a machine in its kind of soldering process. So those are the two big disadvantages, the reason why I didn't use it in the past. But I'm trying to build out a large quantity and have machines surface mounted and stuff like that, so that that's kind of the goal of raising the funds, is actually to buy this part and to solder it onto the board. Now there's some other parts that actually get soldered onto the board as well. We'll take a look at that later. And so yeah, this is just a charge pump circuit, and these two capacitors help create that part of the circuit. And then down here you've got your power jack, or sorry, over here you got your power jack. This is a diode that allows the current to flow this way. I guess technically electrons flow the other way, whatever. And it protects from reverse voltage. So you plug in something that's the wrong polarity, protects from that. This is an over voltage zener, so if you plug in something that's like 24 volts, it'll sacrifice itself so that the rest of the system doesn't die. And then you've got a filtering cap, input cap there. Here's our 5-volt regulator, because that's what our switching system needs to operate on. And so then we get to the switching system. So a couple things here. Let me zoom in on this section. Okay. This is the chip at the heart of the switching system. It's a microcontroller that gets programmed, and it actually is designed in such a way that you could use a non-latching or a latching relay switch. Now, a non-latching switch, what's useful about those is if power gets removed, they revert back to the bypass state. And so that can, if something happens power-wise, it'll just, if it's a true bypass system, you remove the power, it'll automatically switch back into bypass. So that's an advantage. The disadvantage there is that it requires quite a bit of current, 30 milliamps roughly, to keep that switch on when you're using it. And that's quite a bit of power, especially if you're going to power it with a battery. And so if you have a battery powered pedal, you wouldn't want to do that. But it can also work with latching style, which, as the name suggests, as soon as you switch it into one state, it just stays there. It latches into that place until you put it back the other way. And that kind, it works better for a battery. But obviously, if you lose power, it's going to stay in the state that it's in. So, but this can work with both. And so this time around, I designed the circuit board in such a way that you can actually do both. So there's certain parts, I won't go through it in this video, but you can kind of see, like this says latch on it or whatever. There's certain parts that you can omit if you're building the latching version versus non-latching, and then you just change which relay chip you're using. That's not the purpose of this video to go into depth on that, but I did want to let you know that it supports both of those. So then over here, you can see that we've got, this is our high pin. This is the pin that goes high when the circuit is on, and this is pin 5, and then our low pin is pin 7. That's the pin that goes low when our circuit turns on. So when it turns off, it goes up to 5 volts. And then over here, you can see a couple things here. So this is our relay driver MOSFET, and this is for a, what's the word that I'm trying to find for you right now? It's our non-latching style. We'll use this. Our latching style doesn't need it at all. We would omit that part. And so then you can see that up here it says, oh, if you're doing non-latching, you've got this part to add. But if you're doing a latching kind, you wouldn't use that part at all. And all the rest of that's just kind of designed in the circuit board. You've got a diode that protects from that voltage, like that kickback voltage spike that comes from when you kind of instantaneously put a voltage across an inductor. So anyway, so right there, that's like our relay coil, and it's getting triggered, and you can either drive it with that if it's a non-latching, or you can remove that, and use these jumpers, and then it'll be driven directly from the controller, this chip itself, if it's a latching style. Okay, and then, so none of that we've seen so far is actually the audio part of this circuit. That's down here. Let me go down here. Okay, and so this wire that you see coming in here, this is the one that goes high. It goes up to 5 volts when the pedal is off. So it goes up when the pedal's off, so it goes to 0 volts when the pedal's on. And it's feeding this P-channel FET transistor. And so basically this transistor turns itself on when there's no volts, 0 volts onto it, and it turns itself off when there are 5 volts. And the purpose of this is it's this type of switch that is used in like your Boss pedals and other ones that have buffered bypass and use FET switching for its quieter switching. And the goal is to put this is in the, it's in between the output of the effect and the output to the switching system. And so that transition from on and off gets sort of like quieted by this thing turning off and turning on with the relay switch. And so it's done in such a way that it's trying to like time it in a way and ramp it softly, quickly, so fast, but not as like as instant and prone to noises, mechanical noise. And so the goal of this is to soften the click, hence the name TrueSoft. And so that's what it's, this is the output of the board, and this is the where it's coming into the switching system here. Okay, so then this right here is the actual two parts of the relay switch. The relay switch is double pull, double throw. So there's one, there's the other. And then right there is a little slide switch in the circuit that can toggle it's actually in two places, one right there. It's also DBT, DBT on switch. And what it's doing is it's making it so that when your input signal, either when you're in bypass, what happens? Does it go straight to the output signal? Well, that'd be true bypass. And so you can slide it into that mode and it'll go straight to the output when you're in bypass mode. And then when you slide it the other way, what it does is it sends your signal into your pedal, into the audio effect board, and then I've designed in all of the sort of like the standard design, a buffered output pin, and then you can get your signal come out from there, and that's what will come through. Now, that means that on the audio effect board, you have to have a buffer designed. It's not designed in this circuit board, and that's intentional. If there was a buffer designed in this circuit board, then the kind of buffer that is being used, including its input impedance and all its other properties, you'd be stuck with. You wouldn't be able to like create your own or make it match the circuit that you're using. So, so basically it becomes optional. You don't need to use it at all. In fact, there's a way to remove it and put in just 2 little jumper wires, or just like clippings from a Lego resistor, and not have that switch at all. So, so there's, as you can see, there's like so many like options here in this version to just customize it. And I will make a video later when I put out the resources on how to build it about that. You can see here there's an input for if you wanted to battery power it, so that the battery, when you unplug the input jack, it disconnects the battery. And then you would use a TS style plug to plug in so that it makes the ring and the sleeve connect and turn the battery on. That's pretty common in the industry to do it that way if you want to save battery power when you unplug. So that's our input jack, that's our output jack. We've got some 10 meg drop down resistors to when this part of the circuit is not connected to the audio signal. It's pulling down any sort of like stray charge that might have built up. It's pulling it down to 0 volts, so that when you switch it on and off, you don't get like popping. And you can certainly change those values. I chose kind of like the highest functional values, so that your input impedance can be as high as kind of reasonable for this type of circuit. And then you can make it lower if you wanted to. So anyway, if that was too much techno babble, I apologize. It gets a little technical, but there's one more thing I wanted to show you, and that is this pin right here. So a couple things. First of all, you can see there's this 220 ohm resistor. This will be soldered in. It's actually one of the handful of parts that is soldered in, and it's a higher power one to be able to handle what we're going to throw at it. The other side of this you'll connect the LED, the light that tells you if the pedal's on, gets connected to here. One side of the LED is the positive end, anode? I always forget. Why do I always forget? Anyway, and then the negative end to ground, and you can put another, there's obviously a resistor here, but you can also put a second resistor, and I usually do, to reduce the current so it's not crazy bright. Anyway, so there's that. You also want to put that resistor in there, at least another 220 ohm resistor with that LED, so that the voltage right here doesn't get significantly reduced because of the voltage drop of the LED. So just a quick thing there. But if you go see any of my designs, you can see exactly what I've done. But the key element here is that this spot right there, when you have a non-latching circuit, if I can control the voltage right here, I can actually control the whether the pedal's on and off, not from this chip, but actually from the circuit board itself, because a high voltage here would turn it on if it's a non-latching style. And so I use this when I want to do something called true bypass trails. That's what I'm calling it. So that it's true bypass, but it allows the like decay of a reverb or an echo to trail out. And the way that I do it, you can go look at any of the delay or reverb circuits, is basically I use a switch that when a transistor that is connected to the foot switch, so that when I put the foot switch down, that transistor switches on 5 volts right there. So even if it's 0 volts at this pin, or I can point, 0 volts here, it's 5 volts there. That's another reason why this is a higher, anyway. Even if it's 0 volts there, it tries to be 5 volts here. and then it holds this on as long as I'm pressing down on the foot switch, keeping the effect active. And then in the what's also happening inside the audio effect is that the input to the wet signal has gotten cut off, so that the no new thing is. So I've basically turned it into a buffered bypass trails thing as long as I'm pressing down the switch. And then when I let go, this goes to 0 volts, and it turns off the relay switch, and now I'm in true bypass switching. So when I'm playing something that's echoing and I hit and hold the button, it naturally decays, and when I let go, it just transfers over into true bypass. And I found that not only does it work great, the actual switching transition, it tends to be really smooth, because you're transitioning from the buffered effect to a true bypass effect, meaning that the signals are very, very similar to each other. And so when they switch, there's not this like click noise of transition noise. So anyway, so there you go. That is the schematic. Hopefully that helped in some way track down what's going on. Let's go ahead and switch over to the board file so you can see how this is laid out. So first, on this side, on this top facing side, this is all the components that you would install that when I get this manufactured, I'm not going to have installed for you. Obviously, if I'm building the pedal myself, then yeah, I'll put them in there. And I'll have a build guide of like which parts do you need to use if you want to do it in this operation or this operation, like latching or non-latching, whether you have this buffered option or no buffered option, whether you want this soft switch, FET switch or not. Like there's a bunch of different sort of like options, and I'll create a video and a how-to guide on that later. But you can see that there's just not that many parts. And there's even fewer once you consider that no matter which configuration you're using, you're leaving out some parts. And so that was kind of the goal, is to make it so that you could fully customize it, but with as few parts as possible. And then here are your power jack and your audio jacks. Okay, now, let me switch over to, so that's the through hole parts. Let me switch over here to looking at the bottom, which will be mirrored, but so like the text will look off. And you can see that there aren't really that many parts over here, but the ones that are that pre-programmed switching controller, the 5-volt regulator, those protection diodes, and the capacitors for both the charge pump and for the 5-volt regulator. And that's it. Oh, that 220 ohm resistor. So basically everything that shouldn't be customized, shouldn't be messed with, is surface mounted. And so you don't have to think about it. It's already there. And this is also the stuff that is, some of it's like a little more proprietary, or that part literally you cannot order in through hole. It just doesn't exist. And so it makes the build cleaner and simpler. And the other reason why I'm doing it this way, where I have surface mount on one side and through hole on the other, is I want to see if I can keep this available like in perpetuity. And so it can't be that expensive to manufacture. And this chip by itself is expensive already. So I don't want to add too much else to the surface mount part that needs to happen all across the board. And so this is kind of like the bare minimum to make it as easy to build as possible, but to keep the cost of producing another run of them really low. Okay, or at least as low as I can make it. Okay, so there you go. There's the new updated TrueSoft version 2 bypass system. In short, the advantages is that it's quieter, it's more power efficient, it can run, well, the last one could run at 9 volts to 18 volts. Okay, so the advantages are that it is quieter, it's more power efficient. The original TrueSoft circuit could only run at 15. This can run at 18. The original SPS could also run at 18. And then the biggest thing is that it allows for a lot more customization for someone building it on their own. they have more choices on what's important and what's not. And so that also lowers like the upfront cost to get a bunch manufactured. So there you go.